Ultrasonography, also known as ultrasound imaging, is one of the most commonly used technologies for making medical diagnoses. This video will give a brief overview of how ultrasound technology works based on fundamental physical principles. First, let's take a look at the machine itself. With the help of a friction-reducing gel, ultrasound machines use a probe to glide over the area of the body under examination. The probe contains ceramic piezoelectric crystals that can generate and receive ultrasound waves when electricity is applied to them through positive and negative electrodes also within the probe. The electric current causes the crystals to undergo rapid shape changes or vibrations that produce ultrasonic waves. These crystals will also emit electrical currents when hit by an incoming wave, which is why they can be used as a receiver as well. The backing layer and acoustic lens help to prevent backward signals from the crystals and focus the ultrasonic waves, respectively. The probe sends ultrasonic waves of greater than 20,000 Hz, which is a higher frequency than what can be detected by human ears. These waves travel until they encounter an object, such as human tissues, blood cells, or bones, at which point the wave is reflected and then received again by the probe. There are multiple forms of ultrasound tests that produce varying types of images or graphical representations. For example, ultrasound can be used to obtain the speed and direction of blood flow within various blood vessels, or, perhaps more familiarly, ultrasound can be used to produce images of a growing fetus during the gestational period. The transducers use different physical equations to produce different types of images. The Doppler ultrasound, for example, determines the speed and direction of blood flow and is based on the Doppler effect, which can be modeled by this equation. The probe emits a wave with a certain source frequency. When the wave encounters a moving red blood cell, the wave is reflected back to the probe. But because the cell is moving, it observes a frequency higher or lower than the source frequency depending on the direction of travel. If the frequency received back by the probe is greater than the source frequency, then the blood cell is encountering each wave crest at a higher rate than if the cell was stationary. Therefore, the cell must be moving towards the wave source. If the received frequency is lower than the emitted frequency, then the blood cell must be moving away from the probe, and this velocity is reflected on the negative axis of the graph produced. In order for this type of ultrasound to produce an accurate graph, it's important that the probe is angled as close to parallel as possible in relation to the blood vessel being examined. If the probe is 90 degrees to the vessel, then there will be no Doppler effect. Measuring the velocity of blood cells allows one to determine the volumetric blood flow through this equation, where Vm is the max blood velocity, and dividing it by 2 gives the average velocity of blood. Volumetric blood flow is equal to average blood velocity multiplied by the area of the blood vessel. Ultrasonography is the form of ultrasound that most people are familiar with, as it's used in confirming pregnancies and maintaining prenatal health. Ultrasonography uses this equation to determine the distance of different tissue boundaries relative to the probe in order to create a 2D image. Different tissues have different speeds of sound and also absorb, transmit, and reflect waves at different intensities and directions. Using the time it takes for the wave to return to the probe, the distance between the probe and the target can be detected and an image can be created that differentiates between different layers of tissue. Ultrasound techniques can be used to evaluate practically any tissue in the body and are a non-invasive diagnostic tool. In the future, ultrasound technology may aid in the development of accurate 3D bioprinting techniques. Ultrasound could potentially be used to create a detailed and personalized map for bioprinters to use as a scaffold when 3D printing organs for their patients. Thank you for watching my video.